Welcome in this complex analysis class. In this session, we are going to give an example on how to prove Green's theorem in a plane. So the problem is to verify the Green's theorem in the plane for this integral 2x y minus x squared dx plus x plus y squared dy, where c is a closed curve of the region bounded by the curve y equals to x squared and y squared equals to x. Now, when you are asked to verify Green's theorem in the plane, is to show that if you read the statement of Green's theorem, then when you work out the left-hand side, the answer you get is the same as the answer you get when you evaluate the right-hand side. So step one is to write the Green's theorem statement, and then once you have done that one, you sketch the region given for the two curves, and then start working out the left-hand side. After getting the answer, work out the right-hand side of the Green's theorem, and then show your calculation should show that all the two sides converge to the same value. So solution, we know that Green's theorem in the plane states that integral along C of P dx plus Q dy is double integral of the region R partial Q partial X minus partial P partial Y dx dy. So this is Green's theorem in the plane. So that is step one, write the statement. Step two, now let's sketch these graphs. And you see, we need to know the region where we are going to carry out our integration. So that's why it's advisable to sketch that region. So y is given by x squared and y squared is given by x. So this tells us that where this y I can replace by x squared, so that in this one I'll have x squared equals to x. I'm simply replacing x squared for y in this second equation. So this is the same thing as saying x power 4 minus x equals to 0, which is the same thing as saying x into x cubed minus 1 equals to 0. And this is the same thing as saying x equals to 0 or x cubed minus 1 equals to 0. We know that x cubed minus 1 is the same thing as writing x cubed minus 1 cubed, and using the identity a cubed minus b cubed equals to a minus b times a squared plus ab plus b squared. Then this factorization will be x minus 1 into x squared plus x plus 1, and then this should give us 0. So this implies that x minus 1 equals to 0, or x squared plus x plus 1 equals to 0. This will give us a complex value for x, so we are not interested in the complex value of x. This will give us x equals to 1. So therefore, x equals to 1 and x equals to 0. So we'll have when x equals to 0, then from the first equation, y is also going to be 0. So the point 0, 0 is one of the point of intersections. And then when x equals to 1, then 1 squared is also 1. So y equals to 1. So another point is 1, 1. So the point of intersection of the two curves, y squared equals to x and y equals to x squared, 0, 0 is 0, 0 and 1, 1. So therefore now we can sketch that region. So note that y equals to x squared is of this form, and then x equals to y squared is of this form. So this is the two curves. So y squared equals to x, and this other one is y equals to x squared. So these points of intersections, this point here, one on x-axis, one on y-axis. So this is y, this is x. Now let's shade this region. So this region is our region of interest. So the shaded region is our region of interest. And with the convention of positive direction of traversing the region, then it should be clear that this should be the motion, and then this should be the motion. So let's evaluate the left-hand side of the Green's theorem, which is simply the integral along C p dx plus q dy. There are two curves, so we'll have two integrals, one for this curve, another one for this other curve. So this integral C p dx plus q dy will be in two parts, 1 and 2, because that region is defined by two curves. So integral 1 will be calculating integral along the curve y equals to x squared. So this curve here. Curve y along, I'm moving along y equals to x squared. So we are moving from the point 0, 0 to the point 1, 1. So we are moving from the point 0 to the point 1. So our limit of integration would be 0 to 1. And then dy from this one is the same as 2x dx. So that we have the integral along C of P dx plus Q dy will be now integral from 0 to 1. P was given by 2x y, but y is x squared minus x squared, because we are changing everything in terms of x, and then dx plus q was x, so x plus y squared, but y is x squared, so x squared squared, and then dy, but dy is the same as 2x dx. So that's what we have. So when you simplify this, we'll have our value as the first integral I1 would be 0 to 1. So this will give us 2x power 3 minus, this will be x squared. This will be plus x and then plus x power 4. Remember, this is, we have a 2x outside here. So these are 2x multiplying this term. So we'll have 2x times x is 2x squared. 2x times this one will give us plus 2, so this power 4, then power 5. And then dx. So that we'll have the integral I1 0 to 1. So 2x power 5 plus 2x power 3. And then it will be plus x squared. And then everything with respect to x. So this, when we differentiate this, integrate this first term, we have x power 6. 2 divided by 6 is 3. Plus this before 4 divided by 2 divided by 4 is 2. So x power 4 over 2 plus x power 3 over 3. And then from 0 to 1. Now for this integral, the lower limit will be 0 because every term here has an x. So just the same thing as 1 over 3 plus 1 over 2 plus 1 over 3, which will give us 7 over 6. So that is I1. That's the first integral. Integral 2, now we move along the other curve, y squared equals to 1, equals to x. So here, remember we are moving now from the point 1, 1 to the point 0, 0. Check from the diagram. So we moved from here to here along this curve. So now we want to move from here to this point using this other curve. So the limit now will be now moving from 1 now to 0. So will be integral p dx plus q dy along c. We'll have the integral from 1 to 0. Now, y squared equals to x. This means that 2y dy equals to dx. So it will be easier for us now to use y in our integration, and then we fix where this x by y squared. I remember our p was 2xy. So 2 where this x you put y squared, and then times y, minus x squared, where this x squared you put y squared, where this x you put y squared, and then dx. So dx is the same as 2y dy, plus q was x plus y squared. So where this x you put y squared plus y squared, and then where there's dy, we just write dy. So remember, what I'm simply rewriting is that, remember, we had the integral along c of 2xy minus x squared dy dx plus x plus y squared, and then dy. So I'm simply now, because I have y squared equals to x, so it will be easier for me to change all my integral from both x and y variable to simply y variables. Because I know where there's x, I fix by y squared. So this is what I've done here. 2, then y squared times y minus this is x squared, so I square y squared, and then dx is the same as 2y dy. So that's why I have this plus this plus sign. X is y squared, then this was already y squared, and then where there's dy, just write dy. Remember, this is still moving from 1, 1 to 0, 0, still y is changing from 1 to 0. So I'll have my I2 will be now integral from 1 to 0. This will be 2y. Remember, this will be y power 3. So I have y power 4, but 4 was 2 by 2. Y power 4 minus this y power 4, I multiply by this y power 5, and then 2 y power 5, and then this one will give me 2y squared, and then we are integrating with respect to y. So after doing that, we'll have I2 equals to, now this will give me 4 over 5 y power 5 minus, now this will be y power 6, 2 divided by 6 is 3, plus this will be 2 y power 3 over 3, and then 1 to 0. So my lower limit, my upper limit will be 0 minus lower limit, I have just 5 over 4 over 5 minus 1 over 6, 1 over 3 plus 2 over 3. This will give me minus 17 over 15. So that's what I have as my second integral, minus 17 over 15. And so the total left-hand side integral will be sum of I1 and I2. So left-hand side will be the integral is integral 1 plus integral 2, which will be, the first one was 7 over 6, and then plus minus 17 over 15. So 7 over 6 that will give me 1 over 30. So that's my left integral. So right hand side, the last thing is the double integral of partial q, partial x minus partial p, partial y, and then dx dy. So from our question, q is given by x plus y squared, and p is given by 2xy minus x squared. So this implies that partial q, partial x is 1, and this implies that partial p, partial y is given by 2x. So this implies that partial q, partial x minus partial p, partial y will be 1 minus 2x. So this is what we replace here. So we'll have partial integral right hand side of the Green's theorem will be double integral of 1 minus 2x dx dy. Now let's go to the diagram to illustrate how we get the limits both for x and y. So here, to get the limits for x, we are moving the horizontal direction. So from this point of intersection to this point of intersection, x is moving from 0 to 1. So I'll write this one as integral. X is changing from 0 to 1. Now I need now to define the limits for y. Y, remember, y is a vertical change. So we are moving from this curve, this green curve, this red curve, then to this blue curve. So this change will be the value of the function y for this green curve. Remember, green curve is y equals to x squared. And then this other curve, remember, when y squared equals to x, then it's the same thing as saying y is the same as square root of x. This region will take the positive square root. So y is the same as square root of x. So we are moving from this lower curve, y equals to x squared, to the upper curve, which is y equals to root x. So that's what we write. So y equals to x squared to y equals to root x of now 1 minus 2x, and then the x dy. Now to carry out this double integration easily, we start by evaluating the integral with respect to y first, and finally finish with the integral with respect to x. So which will be integral x from 0 to 1, and then y from x squared to y equals to root x of 1 minus 2x, then dy. Remember, we can always rearrange dx and dy, and then dx. So integrating what is inside the square bracket or the this bracket says varies because with respect to y. So just attach y to each of the terms. So we'll have x from 0 to x equals to 1. This will give us y minus 2xy, and then y from x squared to y equals to root x, and then dx. So this will be x from 0 to x equals to 1 of now upper limit will be now square root of x minus 2x square root of x minus lower limit will be y squared, which is y is x squared minus 2x. Where this y, you put x squared, and then dx. So let's simplify this. So x from 0 to x equals to 1. So this will be root x minus, this will be now 2. Remember, this root x is the same as x raised power a half. So let me just write using indices. So like, remember that root x is the same as x raised power half. So I'll have x raised power half. This x raised power half, this x raised power 1. So I'll have minus 2x raised power a half plus 1 is 3 over 2. Minus here, I'll have x squared. Here, I'll have plus 2x power 3. And then this dx. Now, just normal integration here, we'll have now x, and then when you add 1, so we'll have 3 over 2. And then dividing by 3 over 2, we have now 2 over 3. 3 over 2 minus, here adding 1, we have 5 over 2. So we'll have 2 divided by 5 over 2. That gives us 4 over 5. X is power 5 over 2 minus x cubed over 3 plus, so power 4 divided 2 divided 4 is 2. So x power 4 over 2. And then we apply limits from 0 to 1. Lower limit will be 0 because every term here has an x. So just the same as 2 over 3 minus 4 over 5 minus 1 over 3 plus a half. So 2 over 3 minus 4 over 5 minus 1 over 3 plus 1 over 2. That gives us 1 over 30. And you see the same 1 over 30 is what we got for the left-hand side. So just to conclude, since left-hand side equals to right-hand side, equals to 1 over 30, then the Green's theorem is verified. Then we have verified the Green's theorem. The plane. So that's how we solve that problem. Thank you.